Okay, good morning, Astronomy 1010. Welcome to our 8th lecture, where we will say a few short cleanup remarks about the sun. Then we will launch into an overview of the solar system, a couple of announcements. We have a lab today as usual. However, today's lab, we're going to skip over lab 7, I decided, and we're going to go right to lab 8 for now. Lab 8 is on rotation of the sun. So we will want to prepare for that lab accordingly. For the rotation of the sun lab, we're going to track some sunspots. And I'll try to hit print on this now. Actually, I may already have this printed out. What I need is, we're definitely going to need the data sheet. It really would help to have some tracing paper. You guys are going to want to print this page here, and especially this page, these last 2 pages. So this is probably 6 and 7. I just thought to hit print on it now myself. Oh, sorry, 5 and 6. So I'm going to start printing that now since my printer is a bit slow. You guys might want to do the same. This lab requires us to use tracing paper to track the sun. I'm going to take a wild guess that most of you don't have tracing paper on hand. If you do, cool. If not, there are alternatives to tracing paper. You can use wax paper. If you've got some of that in your kitchen, wax paper can be used as an effective tracing paper. Well, probably hard to write on, but you could try it. Also, just a regular piece of paper can actually work as tracing paper. It's just a little bit harder. We'll figure that part out when we get to it. Other announcements. I did not grade your labs and homeworks this weekend because I was a bad boy and I was caught up in Halloween festivities. So I'm going to grade them today after work. It's just going to be a 1-day delay on getting your homeworks and labs recorded. But that should be fine. Hello? Does someone have a comment? Or anyways, I'm going to close that out once I grade those works. Correct. Okay. So last time we left off learning about the interior of the sun. Let's go to one of our slideshows here. My computer seems to be a little sluggish this evening. Okay, or this day. It's not quite evening yet.
I'm sorry, quick question.
Okay.
Did you want 4 and 5 or 5 and 6 for the lab to print out?
5 and 6. You need, well, okay, so hold on. Actually, for you guys, 4, 5, and 6. I already have 4 printed. So the 4, I think, has the pictures of the sun with the sunspots, correct? Yes, say yes.
Yes.
Okay, good.
Yeah.
So
awesome,
you'll do 4 through 6 now that I think about it. Hold on a second. I'm just looking for my interior layers of the sun picture. I suppose this one could do, but actually we'll go with the official one for this course. Here we go. Slide 29.
How would I get page 4 if I don't have a functioning
I'm sorry, Andrew, you're quiet as hell. Can you speak louder to me?
So number 4, I don't have a functioning paper printer. Do you just want me to hand that in?
What do you mean by hand that in?
Like page 4, because I don't have a functioning printer at my house.
So you might have to try to do it using paint on your screen, or how do you normally do your labs?
I just write them down.
So that's going to be tricky. You'll have to just kind of follow along with us as we do the lab, and you'll have to try to take measurements on your screen then, I guess. Andrew, I'm not sure how to do that one. This one is nice to have a printed copy now that I think about it. Sometimes students who don't have access to a printer will open it up in in an image manipulation program like Paint or, Photoshop or something like that? Can you do that?
All
Andrew, okay, let's make this simpler. Just follow along with what I do and write down the stuff that I
right,
write down. Okay? That's how we're
all
going
right.
to. All right. So guys, you can see the interior layers of the star here. The photosphere is, of course, the outer orange surface layer. And then we walked through the convection zone and the radiation zone. These layers of the sun are different because energy is transported through the star by different mechanisms. Do you guys remember by what mechanism energy is transported through the star in the convection zone? This is like supposed to be an easy question, but I don't want to teach you guys too hard after Halloween. Say that?
Convection?
By convection, Noah. Noah, what makes convection different than some other method of energy transport? What have we learned?
Well, conduction's like if two things are touching and you transfer energy like through that way, I think.
That's kind of that's true, more or less. Yeah, I would have liked more detail, but that's good enough. Like if you touch a frying pan when it's hot by accident and you burn yourself, that's conduction, right? Because your hand's touching the metal. So how is convection different than that?
I don't really know convection, and then I just know the last one's radiation. I don't know each one like specifically.
Okay, does anybody else remember what makes convection different than conduction? These are things that we'll want to understand as we study the interiors of planets.
I know you made an analogy like last class about how convection is kind of like the lava lamp.
Yeah, that's a great way.
Will rise and cold blobs will sink.
That's right. So very good memory there, Jake. What makes it different is you're not just kind of touching these hot jiggling atoms, but the atoms kind of form a bubble like a hot air balloon that rises and sinks. And Jake is correct. I used the analogy of a lava lamp, which is an excellent. In fact, you guys might remember the granules. The granules are actually features on the photosphere of the sun. But what you're seeing there when you look at granulation, you're seeing those hot bubbles rising up at the sun. Remember that the typical size of a granule is something the size of Texas, right? And so it's this big fat bubble of gas the size of Texas. Oh, by the way, we got an election coming up tomorrow, right? Woo woo! I hope you're all going out to vote. Speaking of Texas, not that we have anything to do with Texas, but I hear it's close there. And make sure you go out and vote tomorrow. You have the day off for it. And I know it's difficult this year, but it's important to participate in democracy. Anyways, these bubbles, these giant bubbles are rising up from the underlying convection zone. And what makes them stop rising is they get to a layer of the gas that is thin enough that they can start transporting energy by shining away their light. And so it switches over to radiation at that point. But remember that convection is all around you. When you heat up your homes using radiators, if any of you use radiators to heat up your house, you're basically touching pockets of air with metal through conduction, but then the pockets of air become convective and they rise up and they displace cooler air. So that's different because it's bulk transfer. It's transferring lots of blobs at once. If any of you work in pizza shops, you may have convection ovens in there, which are ovens that have fans in them, so they're going to blow hot air around. It cooks the pizza a little faster, I think. And that convection oven is designed to push blasts of hot air against your pizza so that the dough will rise. But for the most part, lava lamps, Jake, are the right idea. Usually conduction only takes place when you have solids. You will discover that the crust of Earth, which is a solid layer, transfers energy by conduction. Because there is no solid layer in the star, our sun, there is no layer of conduction. It's just not an efficient or reasonable method to transfer heat. That's because you're dealing with a gas and you have to have individual particles of gas bop around to each other. In fact, a question that you might have, well, a question that I might have, but you might realize is an interesting question after we talk about it, is why do we transfer from the radiation zone to the convection zone at all at this boundary? The answer has to do with the fraction of neutral gas to ionized plasma. You will remember that a neutral gas has a proton with an electron bound to it. These gases are effective at absorbing photons and heating up to make convective bubbles. When your gases are ionized, the proton and the electron are separate from each other. That means they can't really capture a photon, they can only scatter photons. And that's why radiation or photons transfer energy through the radiation zone. Okay, all of this was just kind of, you know, a sort of review of what we learned last time. Keeping with that review, you guys will remember that we learned a little bit about the nuclear reactions, or we talked about how the core of the sun had nuclear reactions. Okay, my camera is doing an autofocus thing, and it's irritating me. So I'm going to open up Logitech Capture, and lately it's been knocking off my audio, so just hold on a second if my audio goes bad. Okay, we seem to have done all right there. Now my autofocus is deactivated. So let's talk about the sun a little bit more. I thought there would be two things that we could discuss. One was discussing nuclear fusion in the sun. The other thing that I thought I would talk about is I'd talk about the solar magnetic cycle, because Joel asked me a question about that at the end of class last time. So do you guys remember how, well, let's start here. Does anyone know the difference between nuclear fusion versus nuclear fission? These are things that it's good to know about as sort of a general awareness of science. What makes nuclear reactions different than chemical reactions? Can anyone answer that question? What makes nuclear fusion different than nuclear fission? That's another question. Okay, well, let's see if I can help here. Let's find an appropriate slide. Let's find an appropriate slide. Okay, what makes a nuclear reaction different than a chemical reaction is that chemical reactions involve atoms and molecules exchanging electrons. And the atoms themselves don't change. For instance, if you dissociate water into hydrogen and oxygen, the hydrogen and oxygen were still hydrogen and oxygen when they were part of the water molecule. You've just now separated them. In a nuclear reaction, you're actually modifying the bloody nucleus of the atom. So obviously, that's kind of like a whole different level of craziness. Nuclei don't want to be separated that easily, and they can be very energetic when you break apart their structure. There are two different ways to change the nucleus of an atom. One is through fission, which the sun uses, and the other is through fusion, which we use in our nuclear power plants and most of our nuclear weapons. So let's take a look at fission. Fission is when you break apart a fat nucleus. Oh, sorry. Yeah. I think I just said that wrong. I'm a little, that was this weekend's festivities talking out of my brain there. We use fission in our nuclear power plants. The sun uses nuclear fusion. If I said that backwards a moment ago, I apologize. Fission is when you take a big fat nucleus like uranium-235 and you whack it with a high-speed neutron, and you break it apart into what are called daughter nuclei, which usually in the case of uranium, you break apart uranium-235 into cesium and rubidium, both nuclei which themselves are radioactive. And they usually release a gob of energy in the form of gamma rays. This is how we control our nuclear power plants, and obviously the atomic bombs like Fat Man or Little Boy used uranium-235. Nuclear fusion, on the other hand, happens when you take small nuclei and glue them together into a slightly bigger nuclei. Weirdly enough, this also releases energy in the form of gamma rays, but usually a little less. So you can make energy by either breaking a fat nucleus or by gluing little tiny nuclei together. The cutoff for fusion versus fission is the element iron. Iron is a magic nucleus, which can neither experience fission nor fusion. You got to learn about nuclear physics to get that one. Okay, so we use nuclear fission in our nuclear power plants, but the sun uses a cleaner form of nuclear energy called fusion. And the type of fusion that the sun uses is a reaction sequence known as the proton-proton chain, shown here in 2 branches. And I thought that, you know, as your first foray into nuclear physics, maybe we could list the 3 stages of the proton-proton chain. You'll notice here, let's see if I can do a drawing, that stage 1, shown here, and sorry, let me try that again. Stage 1, which is shown here, and stage 2, which is shown here, these 2 stages kind of happen twice, okay? One of the stages is going to involve some exotic particles from nuclear physics. A positron, which is a form of antimatter, and a microscopic particle called a neutrino. I'll try to say a few brief words on those, but I'm not going to go too nuts, all right? Let's just write them down in the following way. How does the sun make energy for sunlight, okay? Basically, the energy of the sun is eventually coming out of the surface in the form of sunlight, which heats up our planet. The answer, so if this is the question, the answer is by the so-called proton-proton chain. And there are 3 steps in the proton-proton chain. I'm going to write the steps out in chemical or nuclear physics notation, which is a little bit confusing, and I'll draw some pictures underneath. So in step 1, we have a hydrogen nucleus, which is a proton, collide with another hydrogen nucleus, which is another proton, and they stick together to form a nucleus called deuterium. Usually I just put a D for deuterium. I'm going to draw the pictures here. They also release a positron, whose symbol is an E with a little plus, and something called a neutrino, whose symbol is the Greek letter nu. We want to draw pictures of these particles underneath, okay? You'll remember that a hydrogen nucleus is a single proton. So I'll draw a single proton here. It's going to collide with another proton there. And one of the protons is going to lose its positive charge, and it's going to become something called a deuteron. A deuteron is a proton and a neutron. Oops, somebody loves me. Hold on. All right, let's get rid of that. That's kind of weird. For a proton to turn into a neutron, it's going to have to lose its positive charge. It does so by the emission of an antimatter particle, Antimatter is basically when you flip the sign of normal matter. So a positron is something that has the mass of an electron, but the positive charge of a proton. Pretty weird, exotic object. Lastly, a neutrino is a little microscopic uncharged particle. It's smaller than a proton or even an electron, and it's basically a little tiny bit of mass that is emitted from the reaction to balance the difference between a neutron and a proton. Let's just write the names of these things underneath. This is called a deuteron. This is called a positron. And this is called a neutrino. I could tell you more about these particles, but it might start to get away from the point of the class. It's all interesting stuff, but I might just kind of leave it there, okay? Basically, some wacky nuclear physics happens that turns two hydrogens into a deuterium nucleus. Remember that deuterium is still hydrogen, it's just a heavier isotope of hydrogen. In step 2 of the proton-proton chain, your newly formed deuterium collides with a third hydrogen, and it makes an isotope of helium called helium-3. Helium-3 is an unstable nucleus that has 2 protons and 1 neutron. Let's draw that picture underneath, okay? So 2 protons and 1 neutron. That technically makes it helium, but it's a very unstable form of helium known as helium-3. It also emits a gamma ray, which is where all of the energy of sunlight comes from. So in the second stage, we emit a gamma ray, and that basically is the energy that will turn into sunlight, okay? In the third stage of the proton-proton chain, these 2 steps happen twice, and you create 2 helium-3s. And in step 3, 1 helium-3 will collide with another helium-3. They will create a proper helium-4 nucleus and leave over 2 protons as a byproduct, which are hydrogens. Now, the moral of the story is that the net reaction, which I had you write last time, the net reaction is that 4 hydrogens create 1 helium and 2 gamma rays. So every day, the sun is converting some of its hydrogen into helium. It's changing its chemical composition, and it's emitting 2 gamma rays as a byproduct. Okay, we're going to leave that module behind. That's as much as I dare say about energy generation in the sun. Andrew, why don't you let me know when you're done copying?
I'm done.
Okay, cool. So I'll erase that in a second. Do you guys remember which layer of the sun sunspots are produced on? On what layer of the sun do we find sunspots? What if that was a test question? Could you answer it?
I think I got you, Brendan.
Okay.
What is it? Oh, is it like on the outside of the sun?
Well, which layer? Because that could be interpreted in several different ways. You're kind of right. What's the name of that layer?
Is it the conductor?
No. Can anyone answer what layer of the sunspots produced it?
Is it the photosphere?
That's right. It's on the photosphere. It's all right. Okay, so does anyone remember why we get sunspots? What causes them?
Magnetic fields.
Excellent, Matthew. Right, the magnetic fields trap some of the plasma. And did we do a sunspot investigation? I can't remember if we got to that last time. That could easily be another test question here. So let's look at some pictures of magnetic field lines in the sun. So here we are, F576. These magnetic fields poke out of the surface of the sun. And as you remember from our lesson last class, magnetic fields can kind of trap plasma. They can stick to plasma. And what happens is at the base of the magnetic fields here and here, you trap plasma at the photosphere, and that prevents the plasma from rising and sinking with the convection zone. And as the plasma sits at the surface, it shines away more and more light until it becomes cooler and therefore darker by comparison. Did we do a sunspot investigation where we calculated the peak wavelength of emission from a sunspot? I can't remember if we did that or not.
I think we did that last time.
Yeah. What was the peak wavelength emitted by a sunspot? Can you answer me that question then?
520 nanometers.
That's the regular photosphere at 5800 Kelvin.
Oh, we did that.
Noah, do you know?
Is it you're asking for the width of the photosphere?
Not the width of the photosphere, but the sunspot. I'm just trying to ask you why sunspots are black. That's why.
I definitely don't think we did that.
All right. Let's do a quick sunspot investigation then. Okay. So let's draw a patch of. So sunspots. I remember last time talking about sunspots, but I was so worried about time, I didn't get into it. They are Earth-sized regions of plasma that become trapped at the photosphere by magnetic field lines. They shine away light to become dark. That's how they cool down. They shine away light to become dark. Other interesting things about them is they always come in north-south pairs, just like a magnetic horseshoe magnet. There's a north pole and a south pole for every sunspot. And the number of sunspots varies over time with the so-called 11-year solar magnetic cycle. The 11-year solar magnetic cycle was discovered by people studying the number of sunspots at the surface of the sun and discovering that they came and went with a perfect 11-year periodicity. That means you get 5.5 years of lots of sunspots and 5.5 years with no sunspots. We are famously in a magnetic minimum now. Recently, there have not been a lot of sunspots on the sun. I've been teaching the class for about 10 years, so I've basically gone through an entire solar magnetic cycle where I watch sunspots increase on the surface of the sun and then decrease. So I've actually gotten to observe this over my career here. I want to show you a picture of the plot of, well, today you're of course going to be doing this in your lab. We're going to track sunspots as they rotate across the surface of the sun, and we're going to use them to track the rotation of the sun. You'll remember that the sun is a differential rotator. It rotates faster at its equator than it does at its poles, but whatever, we'll deal with that. This is a plot of the number of sunspots as a function of time from 1600 to 2000. Do you guys remember who the first person was to observe sunspots in 1600? Who did these? Who did these observations?
Galileo.
That's right. Galileo was the first person to do that. And sunspots have been sort of coming and going with an 11-year cycle. One break in the sunspot cycle came between the years of 1650 and 1700. No one knows exactly why this happened, but we call it the Maunder minimum. The Maunder minimum was a 50-year period where no sunspots appeared on the surface of the sun. Basically, the 11-year solar magnetic cycle was broken. We don't understand why this happened. It's something of a mystery of science. It did correspond to a change in temperatures. Europe suffered a little mini ice age. What the connection is between the Maunder minimum and temperatures on Earth is unknown. People make a big deal out of studying this. That may sound crazy that the solar magnetic cycle was broken for a period of 50 years, but remember that we've only been technically observing the sun for maybe 300-400 years. While that might sound like a lot to you, to the sun, this is a very short period of time. Stars evolve over hundreds of millions or even billions of years. So it could be that these sort of Maunder minimums happen every 1,000 or 5,000 years, and we would not even notice it yet because we haven't been smart enough to stare at the sun and look at these sunspots for that long. But anyways, just to let you know, there are still some mysteries of science hiding out there in the sunspot cycle. I want us to take a look at an investigation of a sunspot. And what I'd like to do is go back to this picture that compares a region of sunspot shown here, which is a cooler bit of plasma, to a normal patch of photosphere. You can see the granules here. This sunspot's at 5,800 Kelvin. And sunspots are usually 1,500 cooler. So maybe the sunspot would be at like 4,000 Kelvin. Oops, sorry. Not so good at drawing with a mouse here. And it's the temperature difference which causes the change in light coming from the sunspot versus the photosphere. So let's try that together. Hey, Jordan, could you bring the temperature down to about 68 for me? Thank you. Okay. Let's do a sunspot investigation. So we have a dark sunspot, and we're going to compare it to a normal patch of the photosphere. The photosphere has a temperature of 5,800 Kelvin. The sunspot has a temperature of maybe, I don't know, 4,000 Kelvin, something like that. Okay. We'd like to ask, one, how much more light does the sun, well, I don't want to say the sun, I want to say the photosphere. How much more light does normal photosphere emit compared to the sunspot. The other question I'd like to ask is, what is the peak wavelength emitted by the spot? And I think this is worth doing because I'm probably going to ask you a test question very similar to this. And you all remember there are tests and they are kind of stressful, right? So we should practice for them now. Okay, how do I answer number one, guys? Suppose I needed to find a formula that measures the quantity of light emitted based on temperature. What formula would that be? What formula tells you the quantity of light emitted from a hot, dense solid based on its temperature? Nobody can answer that?
Is it 3 times 10 elevated to the 6 nanometer Kelvin over the temperature?
That is Wien's law. That's what we're going to want for the
For the
second
second.
question.
Oh, okay.
For the first question, we want to know about quantity of light, which is brightness. Clearly, you guys smoked too much Halloween candy this weekend.
Oh, I got it.
Yep.
Is it, wait, so is it the, what is it? Is it lambda max?
Nope. Nope. That's Wien's law again.
All right. Shoot. No, we did it. Oh, is it, what is it? How more? Is this the one that we, oh no, that's how long. Is it M fusion? Is that the?
No. No, we want to use the Stefan-Boltzmann law.
Oh, Boltzmann.
Does anyone know what the Stefan-Boltzmann law is?
Hold on.
All right, let me help you out here, guys.
B equals the Greek letter that I forgot the name of times
sigma.
10, sigma times 10 to the 4th.
Exactly. Stefan-Boltzmann law. So this is good practice to let you know. You know, the thing about the test question is you got to figure out, when do I use which formula? And that's what this exercise is about. Brightness equals sigma times temperature to the 4th, where sigma, the Stefan-Boltzmann constant, is always 6 times 10 to the 8, 6 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th. That's a formula.
I can't see the bottom.
All right, all right. Actually, I'm going to have to erase and go back up to the top because I'm kind of running out of board space down here. Make sure you guys have all these questions down because I'm going to kind of erase this and use this entire patch of board to answer question 1.
I got it all copied.
Okay, anyone else need a second here, or can I erase? All right. Guys, let me suggest a fast way to do this. For question 1, what we would want to do is calculate the Stefan-Boltzmann law twice. Once for the brightness of the photosphere. So we use sigma times temperature at 5800 Kelvin to the 4th power. And then we would calculate it for the sunspot. We'd use the same Stefan-Boltzmann constant, but now we use a temperature of 4,000 Kelvin to the 4th power. I know for the photosphere, you end up with about 5 or 6 million watts per square meter. But my idea is that we'll just take the ratio beforehand. So I'm going to divide in my mind the brightness of the photosphere by the brightness of the sunspot. And I'm going to divide sigma T to the 4th at 5800 Kelvin, divided by sigma T to the 4th at 4,000 Kelvin. And you'll notice that the Stefan-Boltzmann constant conveniently cancels out top and bottom. Now I could plug in my temperatures, but I'm going to do one more slick Rick maneuver here. I'm going to factor out the 4th power, 5800 Kelvin over 4,000 Kelvin raised to the power of 4. And now we'll plug in our values. Okay. So we have 5800 Kelvin divided by 4,000 Kelvin. Then we want to raise it to the power of 4. Do you guys remember how to take a 4th power with your calculator? What button do I use?
How's my calculator?
What button do I use for the 4th power?
Is it what is it called?
X to the power of y. Let's do it together. 5800 divided by 4,000 equals 1.45 raised to the power of 4 equals.
What is it? How did you do the power 4 again?
I hit this button right there, and then I hit 4. X to the power of y to the power of 4 equals. What's the answer?
I got 4.4.
Yeah. And what is the meaning of the 4.4, Bella? It means 4.4 what? What does 4.4 mean?
I don't know.
A normal spot emits 4.4 times more than a sunspot.
A normal patch of sun. Let's not use the word spot because that's a little loaded, right, Jake?
Yeah.
I understand what you were saying, but Jake is saying a normal patch of the sun emits 4 times more light than the sunspot does, right, Jake?
Yeah, that's what I meant.
Yeah, Jake, you understand me. That's good. So 4.4 times more light emitted than a sunspot. Let's write that down so we understand the meaning. Okay, I need to erase this so I can answer question 2.
All right.
You don't mind? Andy,
So
do you
with the calculator thing, so do you raise them both to the 4 and then divide them?
No, I divide them first and then I raise to the 4. That's why I factored out the 4th power, because that would be less buttons to push.
All right.
You want us to do it again, Andy? Watch my moves.
Yeah.
Watch my moves. Hold on, first I need to get some light here. All right, 5800
Yeah.
divided by 4,000 equals, do you have 1.45?
Yeah.
Now watch, to the power of 4 equals.
Oh, I forgot to hit the, what do you call it, the equal sign.
Oh, yeah, that's important. Okay. All right. Now let's erase this and answer the second question. The second question asked, how does the color, the peak wavelength of sunspot compare to the peak wavelength of photosphere? And for that question, we're going to use Wien's law. Wien's law tells us that the peak wavelength of emission is 3 million nanometer times kelvins divided by the temperature. Now, in order to speed things up, I will remind you that we already did this for the photosphere last week. And when we did this for the photosphere, we discovered that lambda max was 520 nanometers. Do you guys remember what color that is on the visible spectrum?
Green.
That's right. So you guys do remember that. Now let's try it for a sunspot. So of course we would just do lambda max is 3 million nanometer kelvins over 4,000 Kelvin. What's that give us?
750?
Sorry?
750?
Yeah, and what color would that be? Or where is that on the electromagnetic spectrum?
Infrared?
What? I hate when you guys don't give me units.
Oh, nanometers.
Thank you.
Nanometers.
And how about that for color? Where would that be on the EM spectrum?
Infrared?
It's kind of on the boundary, right?
Mm.
Can you hear me?
Yes.
Okay. $750 is kind of at the very boundary of red versus infrared. Shoot, I need to get one more slideshow up. I should have anticipated. It's always good to have the, we depend on knowing about light so much that it's always good to have this slideshow up. I just want to show you guys visually to help burn it into your memories. Come on, baby. That the visible continuous spectrum shown in slide 19, the human eye starts to kind of peter out here, but even though it's infrared, it's kind of just barely at the edge of the visible spectrum, right about here, right? So we could say red or infrared. Either one would be a fair answer to that question. Okay, now, both of these questions, oh, let's put red/infrared. Class, the question I want you to answer is, suppose the sun were covered with one big giant sunspot. What color would the sun be? What color would the sun be if the entire surface of the sun was covered in one big giant sunspot? This is a classic astronomy question.
Would it be black?
Definitely not. That misses the point of the last two questions. Noah?
I don't know. Would it be like green or something?
No.
I didn't finish copying down the numbers. I need to see like the actual wavelength.
Let me give you a second here to do that. So the question, I want you guys to think.
So would it be red?
Still no, not really.
Would it like appear as black because we can't visually pick it up with our eyes?
Guys, it wouldn't be black at all. As you discovered in the previous question, this bugger is still giving off a shitload of light. Pardon my.
Oh, so
If I were to
is it
plot
like,
brightness here, the brightness of 6 times 10 to the minus 8 times 4,000 Kelvin. I don't want to make you guys do it because I'll be here all day. All right, but let's do 6 exp minus 8 times 4,000 to the power of 4 equals. It's giving off, let's see, 1, 2, 3, 4, 15. Wait, is that right? Did I do that right? 6 exp minus 8 times 4,000 to the power of 4. Holy shit. 15 million watts per square meter. Wait a minute, that can't be right. Oh yeah, versus 67. Yeah. Wow. Holy cow. 15 million watts per meter squared. You can't be black if you're giving off 15 million watts per meter squared worth of light, right? That might be a fourth of the normal photosphere, 1.44. We got 4.4 times, right? So this is giving out 4 times more light than that. This is giving out 68 or 69 million watts per meter squared. That's not black. Black is the absence of light.
is it going to be the same, just a little dimmer?
Yeah, Noah. The same, a little dimmer, and you do have a point, kind of redder. In fact, do you want to know what the sun would look like? It would look like this. The filament, the temperature of this filament is very close to 4,000 Kelvin. Let me show you what the sun would look like from outer space. What color would the sun be if it was 4,000 Kelvin covered in one big sunspot? It would be white, just a little bit more reddish. You can see I get kind of a rosy glow here. Ah. All right, so yes, Noah, it probably would look a little bit redder, especially through the atmosphere. But it would mostly be just a ball of light that was still glowing white. So, okay, wait a minute. I'm confused then, Noah. Why do sunspots look black then? I just told you sunspots are white with a slightly reddish hue.
It's just relative to the rest of the sun.
That's right. It's a contrast issue or a photography issue. If I take a picture of the sun so that it's exposed for the photosphere, these guys are producing 4 times less light, so they appear dark by contrast. Very good. Okay, I'm glad we had that talk. Okay, now you've learned a little bit about sunspots. They're not as dark as you think they are. Let me move this lamp before I break it. Okay. I think that's enough to put the sun behind us. And now we can move on to talking about other issues, like the solar system, which is what this class is supposed to be about anyways. So we're now going to transition to a chapter in your book, chapter 7, which is a kind of overview of the solar system. I'm actually going to call up a slightly different image here. I kind of like the one that has Pluto and stuff, the solar system. Okay. I like the image that's in the Wikipedia page. It's kind of nice. Oh, I wanted the solar system with the other stuff too. And one of my slideshows has an overview of the solar system that has more detail. I don't know how I got one, not the other. There we go. This is what I want. Here's an overview of the solar system, slide 6. I don't know how I got one that had Ceres and Pluto and Eris. Before we go into details about the planets, it's good for us to just learn a couple of basic facts about the planets, because it's hard to even get into the details or contrast them unless you know the names of the planets and you know which are the biggest and which are the smallest and issues like that. Here you can see in order of distance from the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Pluto used to be a planet, but now Pluto, Eris, and Ceres are what we call dwarf planets. You've probably never heard of Ceres before, but it's a giant, oversized asteroid. It's the king of the asteroid belt. We can remember the names of the planets with a very interesting mnemonic device. My very educated mother just served us nothing. Okay? My very educated mother just served us nothing. That's how we remember the names of the planets. Let's write them down. So an overview, this is chapter 7 in our books, for anyone who actually reads the book. And that's an overview of the solar system. So we have Mercury, Venus, Earth, Mars. In between Mars and Jupiter, we have the asteroid belt. And then outside of the asteroid belt, we have Jupiter, Saturn, Uranus, Neptune, and then at the edge, we have objects like Pluto and another dwarf planet called Eris. But it's not just Pluto and Eris out there. There's a whole bunch of giant oversized comets called the Kuiper Belt. The Kuiper Belt is a disk of icy objects that are kind of like Pluto and Eris, and it's one of the 2 reservoirs of comets in our solar system. The Kuiper Belt is in the same disk as the solar system. There is yet another more deeper reservoir of comets that's really, really far outside the solar system. I'm just going to put them up here, but they actually go around the entire solar system, and they are known as the Oort cloud. This is everything that's in the solar system. We have the planets, the asteroid belt, the Kuiper Belt with Pluto and Eris, and the Oort cloud. You guys probably haven't heard of the Oort cloud before or the Kuiper Belt, so I think a picture would be helpful here since my picture is lacking. Let's see if we can go to one of these images. Ought to do better than my drawing. What do I like the best? Or rather, what do I hate the least? Maybe this one. This one attempts to show them in scale because the scale is actually pretty dramatic. The box is a zoom in of that little blue box there, showing you that the Kuiper Belt are icy comet-like objects that orbit in the same disk as the solar system. But the Oort cloud is surrounding the solar system in a giant spherical distribution. You know, there could be like these giant icy objects all the way out to the next star, Alpha Centauri. Perhaps interstellar space isn't quite as empty as we thought it was once. Okay, cool. Now, there are different types of planets in our solar system, and we're supposed to learn a little bit about them. These types of planets are called terrestrial planets, and these, or rocky planets, these planets are called gas giants or the Jovian worlds. Let's write that down. Terrestrial planets versus the Jovian planets. Sometimes we call the Jovian planets the gas giants. All right. Could I list some details? Terrestrial planets versus gas giants. The first would be their composition. Terrestrial planets are made of rock and metal. But Jovian planets are mostly made of hydrogen and helium gas. And they actually don't have solid surfaces the way our planet does. Another thing that distinguishes terrestrial planets, something that we'd like to make a big deal about, are the densities. Does anyone know what density means? Here's a piece of rock that makes up most of the terrestrial planets. It's a piece of granite. I think like 80 or 90% of the surface of Earth is covered in granite. Well, that and basaltic rock, I guess. But when I talk about density, what do I mean by density?
Like the amount of matter in a set volume.
That's right. It's the amount of mass contained in a certain volume. But that's similar to what you said. So terrestrial planets have what we would consider high densities because they're made of rock and metal. The typical density of a terrestrial planet is usually around 5 grams per cubic centimeter. We tend to measure densities in grams per cubic centimeter. Jovian planets have low densities. 1 gram per cubic centimeter is a typical density for a Jovian planet. And by the way, that also happens to be the density of water. Water has a density of 1 gram per cubic centimeter. That does not mean Jovians are made of water. It just happens to be that way. It's kind of tricky. Density turns out to be a key indicator of the composition of a planet. All right, so one's made of rock and metal, the other's made of hydrogen and helium gas. Let's talk about other points that matter here. Terrestrial planets, well, how do I want to do this? Terrestrial planets are close to the sun. That's kind of obvious. Jovian planets are far from the sun. And that is a question that we would like to ask ourselves. Why did all the small rocky planets form close to the sun and all the big fat gas giants form far from the sun? Is that random? Hell effing no, it's not random. If it was random, you'd expect there to be a smattering or a mix of terrestrial versus Jovians all the way out. The fact that you got 4 on one side and 4 on the other side, that means there is some logic to this that we'd like to discover. Obviously, the terrestrial planets are small. The Jovian planets are large. How about moons? How many terrestrial planets? Let's see what you guys know about our solar system. How many of the terrestrial planets have moons?
One.
False.
Oh.
False.
3.
False. I guess you've answered everything except the correct answer, right?
5.
Well, there aren't even 5 terrestrial planets.
2.
2.
Thank you. Which 2 have
We're
moons?
so smart.
That's all right. You got. This is why we have to have this chapter, so you can learn some basic things about the solar system. Which terrestrials have moons? Obvi, Earth has a moon.
Venus and Earth.
No, not Venus.
Oh, I was so sure.
Mars.
Mars. I don't suppose you guys know the names of Mars's moons, do you?
No.
Phobos and Deimos. You know, you guys should really watch this cool sci-fi TV show on Amazon Prime called The Expanse. I love The Expanse. It's a really cool show, but what's nice about it is it's like a murder mystery that takes place across the entire solar system. So they've got people living in the asteroid belt and some people living on Mars and Earth. And honestly, if you don't know anything about the solar system, you'll learn a little bit. And it's a cool aft science fiction show. All right. Anyways, there's my plug for The Expanse. I want to show you guys a picture of Mars's moon Phobos. It's, well, let's see what you guys think. This is what Phobos, the moon, looks like. It's different. What does this look like to you guys? This thing is only about, I think, 20 kilometers across or so.
That looks like what I've always seen depicted as an asteroid.
Yeah. And there's a reason for that, Joel. Because it is a freaking asteroid, probably. You'll remember that Mars is very close to the asteroid belt. And probably what happened is at some point, well, this doesn't show the asteroids, but it probably at some point, one of those asteroids just wandered over and got captured by Mars. And the other moon is even smaller than that one. So even though Mars has moons, it's technically just like a glorified asteroid. That's all it is. In other words, moons are actually not common for terrestrial planets. So terrestrial planets have few, or in most cases, no moons. In fact, you're going to discover later on that Earth's moon is actually kind of stupidly big for a terrestrial moon. Our moon is comparable to some of the larger moons of Jupiter. Our moon, the moon, is about the same size as and the same mass as the moon Io around Jupiter. And that's one of Jupiter's largest moons. So there's no reason. Yeah.
So if Phobos, or whatever the name of that thing is.
Deimos.
Okay, yeah. If that's technically an asteroid, does it function the same as Earth's moon?
It might not function the same. I guess it depends what your function is. You know.
Well, I mean, like does it like Earth's moon gives off light or reflects light from the sun?
And so does Phobos,
right?
Just less.
Okay.
I guess a question that you might ask is, if I'm standing on Mars, what would Phobos look like? The answer, Joel, is that Phobos is so small in size that it would probably look more like a star than it would like a moon. And that's just because it's so tiny. You know, that's a great question. I wonder if we can get a picture. Hold on, I'm going to sneeze here. Woo!
Yeah, that was what I was trying to formulate.
Remember that we've got some rovers on the surface of Mars. I wonder if we could see a picture of Phobos moon from Mars. Let's see if, I don't think it would actually look resolved. I think it would be a point source, but I want to fact check that. I'm not, I used to know the answer to that, but I forgot. Come on, internet. Can Phobos, here's a Mars moon Phobos eclipse. That might answer our question. Oh, wow, this is cool. This is Phobos transiting the sun. I bet it looks like a little tiny black dot. And this is seen from the Curiosity rover, I think. This is only 54 seconds. So, oh, look. So that's actually bigger than I thought it was going to look. That's kind of cool. Maybe it can be resolved as a disk. You know, that would be a problem for the small angle formula. We could actually do that by getting its distance and its radius and computing the angle. If it's greater than 3 arc minutes, it can be seen. But I don't know if I have time for that today because we're almost out of time. Jovian planets, on the other hand, have tons of moons. So unlike terrestrial planets, I think Jupiter has like 60 something moons. Saturn has 60 moons. Uranus and Neptune have maybe 20 or 30 each. They have so many moons. So many moons. As you know, no terrestrial planets have rings. Not yet, anyways. At one point in the future, one of Mars's moons is going to disrupt and turn into a ring of dusty debris, but we're not there yet. How many of the Jovian planets have rings?
1, Saturn.
It looks like that from my picture, but it turns out that all 4 Jovians have rings. You've just never seen them all before because they're faint. What is correct, Andrew, is that Saturn has the most prominent rings, and therefore they can be seen through a small telescope on Earth. But if you take a trip out to the Jovian planets, you quickly discover that they have rings as well. They're just very faint. Here's an iconic picture of Jupiter's rings as seen from the Galileo spacecraft. Yeah. If you travel behind Jupiter and watch Jupiter eclipse the sun, you can actually see the faint ring system around Jupiter. Legendary photo from astronomy here. The rings of Neptune and Uranus are harder to see, and we have not had a modern space mission out there since the Voyager. But we can see, I think if you look in the ultraviolet maybe, or maybe it was the infrared, I can't remember. One of those 2 wave bands, you can see the rings of Uranus here, but they're not easily seen in visible light. Neptune's rings are very, very hard to see. We did get a picture of them during the Voyager mission, but it was quite difficult. We had to block out the light from Neptune in order to see it. All 4 Jovians have rings. And at some point, we'll probably want to talk about what makes those ring systems. Okay, there's more to do on the solar system, but we'll have to have that wait until Wednesday after the election. You guys know we're going to do our rotation of the sun today. I was thinking we'd stop a little early and just kind of take our 15-minute break. That way we can get back to business right around 1-ish or a little after 1. Does that sound good for everyone?
Sounds good.
Yeah. Okay. Okay. I'm going to take a pause, and I'll see you guys in a little bit. Okay, Astronomy 1010, we're back. We are about to do lab number 8, rotation of the sun. That means we've skipped over lab 7 because I think it's better that way. I don't know. We might come back to lab 7 eventually. We'll see. To do today's lab, you're going to want a few things. For the lab packet, which I attached to the Blackboard handout, we have a few images, black and white images of the sun with some sunspots on them. We're going to need that paper. We're also going to want to use our data sheets, which are 13.5 and 13.6, right from that lab handout. It would be also really helpful to have some tracing paper. I know most of you won't have that. You could either use wax paper, or you could use from your wax paper from your kitchen. You could also use just a regular piece of paper, especially if it's a bit more translucent, okay? We're also going to need a ruler, a protractor, and it would be very helpful to have a compass as well. Here's my pencil, my eraser, in case I need them. Sharpen that up. Let's see here. I'm going to start by cutting off a square of paper, and we're going to be tracing some sunspots. Here's one from an older lab I did. It's going to look like this. So it looks like the length of this square, which is ideal, is about 10 by 10 centimeters. Excuse me. I'm all kinds of messed up here. So I'm going to make a mark here with my pencil. What did I do with that pencil? Oh, there it is. Okay. See if I can't make a square that's about 10 by 10 meters. And a pair of scissors will cut that up. Here we go. That away for later. All right. Let me get my phone because we might need that. Let's see here. All right. I need to activate my Wi-Fi. Sorry, guys, I'm just moving a little slow today. I'll catch up here. Get my roll of tape, which is always helpful and handy to have. Okay, so let's look at, let me move this out of the way here. Let's look at our lab handout and let's see what we can see before I go to this here. Our goal is to track pairs of sunspots as they rotate across the disk of the sun. You'll remember that sunspots, let me clear that, they oftentimes come in pairs. Our goal is to track one sunspot as it kind of moves across the disk of the sun. The eventual goal is to find the rotation rate of the sun. Does anyone remember how long it takes the sun to rotate? It changes depending upon the latitude. Well, I guess you'll find out in today's lab. We're going to track one sunspot as it rotates across the northern hemisphere. And we're going to track one sunspot as it rotates across the southern hemisphere. And I'm going to tell you which spots I think we should track. The one in the northern hemisphere we'll call the A spot. The one in the southern hemisphere we're going to call the B spot. And by taking the average, we should get a pretty effective estimate of the rotation rate along the equator of the sun. That's what I'm hoping. Let me clear out this drawing. I'm going to cut down on our tabs to improve our bandwidth here. I think these cut into our bandwidth. Come on. All right, so why don't we go over to this page? This is where we show the sunspots that we're planning on tracking. Now, I'll circle them in a moment, but I want to try to find the brightest, or rather the darkest spot on each image. And on the first set of 6 days, you can see the dates are listed below here. This is the darkest sunspot here, which if you see these two sunspots there, they're the same as those two sunspots. So that spot begins there, there. It goes to there, and then finally to there. Let's circle those on our paper. I want to see if I can switch over to my phone here. Let's see how my share feature works.
Oh,
Sorry, hold on. I've got to install the plugin again for some reason. Makes me install the plugin every time. Luckily, that doesn't take too long. Okay. Sorry guys, it's doing the thing where it's not connecting for some reason. Let me close some stuff on my phone, see what's going on. I am connected to Wi-Fi. Let's try stop share. Let's try doing it here first, and then we'll share screen. Okay, we got a problem, Houston. We are going to need this phone here to do this. So let me turn the power off. While I'm turning it back on, let's see if we can track those sunspots on the digital copy instead. So there's no sunspot on the first day, 725, but on the next day it goes there to there. I'm putting a big circle around it so I can find that spot later with my tracing paper. To there, to there. That's going to be our first spot. That's the so-called B. Oh, that's the second one. That's the B spot. I'm going to turn my phone back on while you guys get that. I'm choosing spots so that we get a good coverage of the northern and southern latitudes. That's the idea. Sorry, my Apple, my phone is just turning back on here. Okay, let's see if we have better luck now.
Oh, can I? Oh, shoot. I
Sorry,
wasn't done copying.
that's okay. I'm going to do it again with my phone, Andrew. Okay.
All right.
Share screen. What we got to do is get this phone working so that we can prosecute the lab here. All right, there we go. Jeez Louise. Come on, baby. All right. Okay. Okay, so let's do this right. Let me get my pencil. So the first day is, oh, am I upside down here? Yeah. I'm upside down. So there's no spot on the date 725, but the sunspot on the bottom hemisphere begins 727. It's that one. I'm just putting a big circle around it so we can quickly find it later. Then it moves over to here.
Wait, there's no seven. Wait, hold on.
The very first window does not have, well, it has sunspots, but it does not have the spot that we want to track. Okay.
All right.
The spot that we want to track, which I have declared the spot because it's the darkest in later images, that spot appears here. And you'll notice there's two over here. That helps me locate this spot later on. Because when we move from 727 to 730, I can see those two there. And now my spot has become a bit darker. On the next day, on 8-1, it's the dark spot in the middle. On 8-3, it's the dark spot there. And on 8-6, it's the dark spot there.
Oh wait, the one after 8:30 I need. What's
There is no 8:30. There's 7:30.
Oh no, I meant 7:30, not 8:30.
There's 8-1.
Oh, I got it.
Eight 6, 8-3. Are you good, Andy?
8. Yeah, I'm good. I'm good.
All right. Now let's go down to 8-8. We want to track a spot in our northern hemisphere, and that's the dark spot that you see there. Okay. That's 8-8. In the next image, we go to 8-10. And on 8-10, it's this dark spot there. Now let's slide
Where is it on 8:10?
right there.
All right.
Top left. 812. It's the dark spot that we see there.
All right. Oh, what was 812? Oh, wait. Oh, I need 812.
That's 812 right there.
All right.
Can I go on? 814, the dark spot there.
2012. What is it? 14.
Oh, you're probably making this by hand. That's why it's taking a while.
Yeah, yeah.
All right, I get you
sorry.
now. I'm sorry, Andy.
Yeah, I was gonna ask that because I didn't know if it was like a terrible time to bring up the top that I don't have the paper, but
Yeah, I'm doing that too. I'm doing it by hand.
Look, just take the cap of a peanut butter lid, or I've got these circle makers, and just make a bunch of circles. Honestly,
on a paper, like,
guys, I got a better idea. Why don't you just follow along with my measurements, okay?
all right.
Actually,
I was about to
Jake, I
use an
appreciate
old
you-
honeydew cup to do it, bro.
All right, well, hey, either you do, or you don't. You know what I'm saying?
I agree.
Okay, all right, so there's 814.
Stick with your day job, Brendan.
Yeah. I want to take this operation down to the comedy connection once it opens back up, right? There's 816 right there.
Oh, 816.
And and at 818, it's the dark spot there. So that's the bottom row.
Wait, so you got 8, where's 816? 20. Oh, 8. Or no, the one after that, I got 816.
That's 818 right there.
8. There we go, I got them.
Okay, cool. And like I said, if your picture comes out sucky, well, you can just kind of follow along with mine, okay? All right, now, before we can begin, we need to make an exact model of the sun on tracing paper. And rather than try to hand trace it, which would be crude, I'm going to measure the sun and I'm going to use the compass to make a perfect circle of the same width. When we measure astronomical objects, we always want to attempt to measure them vertically because they can develop errors due to the lots of astronomical objects bulge along their equators. So measuring vertically is the better way to go. How many millimeters would you say is the diameter of that sun? How many millimeters is that?
54.
Yeah, I'd say that too. I'm just going to make note of this. This is 54 millimeters. So what would the radius then be if we wanted to make the radius of the sun?
27.
Yeah, 27, right? We're going to make a line 27 long. Let's go ahead and do this. So I'm going to do it up at the top. I'm going to make, watch me do this now. I'm going to make a tick mark, right? I'm going to keep this clamped down. I'm going to make a vertical tick at 0 and a vertical tick at 27. This is how I'm going to set my compass.
Where is it? 20. Oh,
It's
shoot.
2 ticks after 25 here. Just take a look at that.
Oh, my shit's all squashed up.
Okay. All right. Just stay cool, baby. We got this. You guys probably don't have a compass anyway, so you're probably going to have to watch me do this. Let me see what's going on in the chat window there, which is...
Oh, wait, I found a way to do this.
725. Cam, just ask me, I'll tell you. There is no dark spot in 725. That's the first, the dark spot didn't appear on the southern hemisphere until 727. So I've now set this to 27, I believe, let me verify, 27 millimeters, okay? And I'm gonna set my compass, my radius to that, put the point here, and then I'll slide until my compass is right at 27. I'm gonna test and make sure it comes out right. Could be a little sharper, there we go. All right. Now, it really helps to have some padding. Don't just try to, if you do have a compass, which you probably, most of you don't anyways, but I like to use a bit of notebook before I make the circle here. And you can check out my moves here. I'm going to pin it and spin it. I'm going to pin it down, rotate with my hand. It's fun to make perfect circles. It's a pleasing, enjoyable exercise. Okay. Let's see how I did. First, I'm going to clean up my edges a bit here, just because I got a bit of OCD like that. Okay. Flatten the curve, as they say. All right. Better. Let's see how. Ooh. Let's hold it up to one of the suns and see if I got it right. And if you've actually made a circle, you have to check and verify, make sure that it actually lines up. Now, you guys can see that there are some tick marks here. This is an important thing. We're going to have to trace over the 4 tick marks, north, east, south, and west. And those are going to be our registration tick marks. We're going to make sure that each time we register the sun to those tick marks, they've flipped, all telescopes invert images. So east is on the left because they originally imaged the sun upside down and then they flipped it again for you, which I think is what put east on the, does that make sense?
Yeah, it does. Mine's kind of flipped.
Okay, yeah. Yeah, because if you upside down it, then east would be on the right. Okay, anyways. So now it's time to track some spots, okay? Let's do that. So the hemisphere, the southern hemisphere spot, the first one we do is going to be our B spot. So I'm going to register my tick marks first, carefully. And then I track my spot. And underneath each spot, I'm going to put the date as a month / a day. So that's 7/27 is my first spot. Tracking my first spot. Let's go to my second spot. We'll sort of cover our registration ticks. It's really important to use the registration ticks so you don't accidentally drift north or south during this process. It's very easy to do that. This next one is 7:30.
Will we get points off for not having that our own little circle thing?
What do you mean our own little circle thing?
Like if we don't have a compass to draw a perfect circle like that, and we use your measurements, are we going to end up getting points off?
No, we can use my measurements. I wonder if I could scan this and send it to you. What's the best way to do this? Well, I guess if you don't have a printer, then it, so do you, let's ask this. Do you have this printed out?
Yeah, I do.
Take another piece of paper if you want to do it right and at least try to trace over it with your hand. That's one way you could do it, right? You could take a cue card, you could take a simple piece of paper, and you could cut out a square of the same size.
I'm sure that there's people that don't have it though, like for them too.
Yeah, what if you live in the Stone Age and don't even have the paper with the circles on it?
Well, then you're just gonna have to follow me.
All right.
Follow me. You're right. Okay. So I understand that a lot of you guys don't have stuff.
My apologies.
That's okay. Why don't you just follow along? Following along with my measurements is fine. Okay. Just
Thank you.
maybe just watch and then write down when you can write down stuff. Just do something and show me something. Okay. Try to.
I'll be productive.
Yes, that's what I want to hear. Okay. Do whatever you think you can do. So here's 730. Okay. I'm going to go on and trace the next spot. Okay. Okay. 8-1. Okay. Let's move on to this next dude here. Track 8-3. And lastly, get these registration ticks going. Ooh, it's tight. And here's the last one. And that's 8-6.
Wait, can I see that? Oh, wait.
So,
No, the little parchment paper or whatever.
that's
that
what I got
is.
so far. I track. So this is my B spot. I'm going to call this my B spot over here. The one at the top, I'll call the A spot. All right, we ready to track the northern hemisphere spot now?
Up 727.
That was spot A, right?
No, that's spot B. So the reason we did B first is, follow me here. Do you see how this one is in the southern hemisphere and the one below the northern hemisphere? Just out of tradition, I always put the northern hemisphere spot as the A1. I didn't have to do it that way, but I did. Excuse me. All right. Andy, can I go on here?
Yes, you can.
All right, let's go and track that A spot, which is actually the second one. So I'm going to start on date 8-8. I'll get my registration tick marks in order. And I'll track here. Okay, that is 8-8. Gonna have to write really tiny here. And this is how people actually measure the rotation of the sun, believe it or not. By tracking sunspots, 8-10. I don't like how close that was, but I'm not going to erase it. It's going to smear. Over here. Track this bad boy. This is 8-12. Okay. Go down to the lowest one. Okay. That's 8-14. Oh, sorry. Okay. Here we go. That's 8-16. And the last spot. This is 8-18. Get those registration tick marks lined up. And one last spot. That's 818. Okay. And this is going to be our A spot. So at the end of the day, this is what I got.
Yeah, my last tick mark for A is kind of a little bit off the page, but I drew a line.
That's okay.
What date?
Well, we're going to actually need to draw a best fit line next. So I want you guys to watch what I'm doing here. I'm going to draw 2 best fit lines through these sunspots, okay? So I'm going to take my ruler. I'm going to try to force the line to be horizontal. So it's going to be a horizontal best fit line. Best fit line means equal numbers of spots above and below. So let's see if we can do this right here. I'm not going to stand up. And I'll make my best fit line like something like that. It does not go past the edge of the sun. It just does that. Okay, so that's my A spot, best fit line. Notice I've got equal numbers above and below roughly. Now I'm going to do my B best fit line. Make it horizontal, equal numbers above and below. To the best of my ability. Yeah. All right.
Oh, one of my dots are not connecting. Oh man.
The dots, the sunspots drift a little bit in latitude. That's why we have to make a best fit line, because they drift a little above and below the line, as you can see.
Oh, I see it now. All right.
Okay, now we have to measure these lines and transfer them to the paper. So hopefully you guys have a ruler around and you can at least do this part. Let's use our A spot and measure that line together, okay? What would you guys say is the length of our A spot line?
It's 5 centimeters or 5.1 if you want to like.
Yeah, it's tricky, huh? Okay, let's go with 5 centimeters or 50 millimeters, okay? Make a line directly to the right of spot A that's 50 millimeters long. So where it says spot A, make a line of exactly that length just to the right of spot A, just like I did. Now
this is the northern hemisphere one?
The northern hemisphere one, right.
Okay.
It's about 50 millimeters. Now we got to find half this line and we got to measure it. So half of 50 is 25. So make a vertical cross that will not be confused with a spot. Right at 25. And now I'm going to use my compass to kind of turn this into a semicircle. I'll explain this in a minute. So I'm going to put my pointy part here. And I'm going to set my compass radius. And I'm going to try to draw in a semicircle.
Oh shoot. My semicircle might go into my angular velocity.
Well, that's why I told you to put it right there and not too far to the right, you know? That's going to create some problems for you later on.
Yeah.
You might want to put it where I told you, which is directly to the right of spot A.
Oh, I got it.
Let's do the same for B, and then I'll tell you why we did that.
Ava's been trying to tell you she doesn't have the right tools, and she wanted to know what she could do.
Oh, well, Ava, it would have been nice if you talked to me because it's hard for me to check this thing. Like I said, Ava, well, I don't know, Ava, what do you have? What can you do? Let's start there. What can you do, Ava? If I were you guys, if I was a student, I would try to do whatever I could. I certainly would expect you guys to be able to do this page. These are the 2 pages we're going to turn in. So we should put our name up here. Please do not screw this up. We are submitting Lab 8 today. I know about 5 or 10 of you are going to submit this to Lab 7 because people are just bad at following instructions. That's just a thing about life, that people don't really listen. They don't really follow instructions. But it would be really cool if you could all remember to submit this to Lab 8 and not to Lab 7. Okay, and your section will be AS1010, whatever your section is. So Ava, because I can't hear you or see you, I don't know what you can do. Like, you should have this paper at least. To do this part, I would have tried to cut out a piece of paper and I would have tried to trace over these things. And I would have, some of you are clearly trying to follow along as best you can. At some point though, you're kind of following me and you're taking my measurements.
How long is the line next to spot A again?
It was 50 millimeters long.
All right, thank you.
She said she only has a ruler.
Okay, so here's how I would do it. I would draw a line that was 50 millimeters. And then to make the radius, I would measure 25 millimeters from the center and make a whole bunch of points. And then I would connect the dots. Let me show you a clever way you can do things with a bit of imagination. If you don't have the right tools, I would do this. Okay, here's how I would attack the problem. I would use my ruler to make a line that was 50 millimeters long, and I would get creative. I would make a mark at 25, right? And then since I didn't have a compass, well, I have to work harder at it. I would find a line 25 millimeters from the center, and I would make a bunch of dots there. So I'll make a dot here. That's also 25 millimeters from the center. And I'd make a dot vertically that was 25 millimeters from the center. And I would make a dot 25 millimeters from the center here. And I would make a dot that was 25. And this way, without a compass, I could connect those dots. Let's do one more. Let's do one more there. With enough dots, I'd be able to kind of just draw the line in. And now I would kind of connect the dots with my pencil to make my, see that?
Damn it, my paper ripped.
Uh-oh.
Oh, shit.
See that, Ava? I'd kind of do something like that. Would it be perfect? No, but it would be better than completely freehanding.
I got so lucky. I found this perfect thing to make circles. It's like what holds light bulbs in their boxes.
Oh, really?
Yeah.
That's great. See, now that's being crafty and creative, right? You got to be like a scavenger of the wasteland here. You got to grab whatever tools you got and use them. Just like you were in the post-apocalypse. Because you pretty much are in the post-apocalypse. Okay, Ava, I hope that answers your question. Back to the game. Let's measure our B spot. Okay. So put 0 there. What would you guys say the length of this line is? Kind of messy there.
48 millimeters.
Good. Let's make a line that's 48 millimeters here next to spot B. Carefully measure up to 48 and no more. Half of 48 is 24. 24, right. I knew that. I was just testing you. Okay, and now I'm going to make a mark at 24. I'm going to use my compass or the dot method, Ava, to draw in the radius here. set my compass. And
You said that one's 4 centimeters?
no, I'm doing it in millimeters, not in centimeters.
Oh, 40?
48.
Oh, 48. Okay, thank you.
Okay, let me explain what these two things are. The sunspots are obviously rotating across the face of the sun, which is a three-dimensional thing that sticks out like a belly, right? We're trying to imagine slicing the sun at these latitudes and then creating a top-down bird's eye view projection. So this is a cut through the sun, and we're looking down at the protuberant belly of the sun that's poking out into outer space. And we want to try to track our sunspots first onto this line and then up to the surface of the sun. First thing I'm going to do is I'm going to get some padding. I'm going to use this kind of squishy notebook underneath it. And I'll place my paper on top of that squishy notebook. And now to track my sunspots, first I'm going to overlay my A line and just kind of check that it works there. All right. So these kind of match up more or less. And what I'm going to do is I'm going to take a pokey, sharp pin. I'm going to take the pointy part of my compass and I'm going to stab through the paper and stab the sunspots onto the line. So I'm going to poke through and go dink, dink. I'm going to force them to be on the line. Dink, 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 dink. Those are the sounds of me poking through the paper. And you'll see I've left some spots below that I can now color in with my pencil, and I can transfer the dates to the spots underneath. Okay, so I've got 8-8. I've got 8-10. I've got 8-12, 8-14, oops, 8-16, and lastly 8-18. Jordan, do you want to bump it up to like 70? I'm getting cold again, sorry. Maybe 71.
Oh.
All right, let's do this for the B line next. So I'll just make sure that my B line matches up. Hopefully they match up on your end too. I'll poke through. Dink. 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 And dink. Okay. And let's get these dates on here. So I've got 7/27, 7/30, 8/1, 8/3, and 8/6. Okay, let me explain what our procedure is going to be. Our goal is to measure the rotation rate of the sun. And you might think, hey, bro, can't I just track a sunspot all the way across the surface? Well, you can't, because once the sunspot gets to the edge of the sun, it disappears from view and you lose track of it. What we're going to do is we're going to watch a sunspot rotate through a small window, and we're going to attempt to calculate the average angular velocity. So hear me out on this and see if this makes any sense, right? Imagine that this was my sun. And imagine we can only watch a sunspot rotate through a small fraction of the sun. So I can watch a sunspot start maybe here. And it can only rotate to say over there. And what I want to do is I want to track how many degrees does the sunspot rotate per day. So for instance, if it takes 2 days and it rotates, say, 10 degrees, I would know that my sunspot has an angular velocity of 5 degrees per day. And then I could make an argument and say, if it goes 5 degrees in 1 day, that should be equal to 360 degrees in some unknown period worth of days. So 5 degrees is to 1 day as 360 degrees is to the period for the spot to go all the way around the sun. Then I can solve for the period as 360 over whatever the angular velocity is. Sometimes we use the letter omega for angular velocity. Okay, so what we're going to do is we're going to track 2 of our sunspots up to the surface to try to get its angular velocity. So let's pick 2 sunspots on either side of the center. I'm going to pick 810 and 816 because those will be easy to measure. And I'm going to track the spot right up to the surface of the sun, but no farther. There and there. So I've tracked them up to the surface. Now I'm going to make a line that goes from the center of the sun through the intersection of the sunspot with the surface. And I'm going to let that line go out really far so that I can measure the angle pretty carefully. So there. And there. Notice how far out I've extended those lines.
I don't know if I can extend them that far.
Why not?
I did it.
Did you not make your line right next to spot A like I instructed you to?
Let's just say that paper is not in my grasp at the moment.
Okay. Well, were you able to print? You couldn't print this out?
I can't print anything, so I did it all by hand.
All right. Well, who are you, by the way? I don't even know who you are.
This would be Greg.
Speaker Greg. Okay. Well, Speaker Greg, do what you can, okay?
I can make the lines, but I can maybe go out of that semicircle. I don't know if I can go any further than that. On one side, at least.
Oof. That's going to lead you to some problems. You might want to put it over another piece of paper underneath.
All right.
You'll notice in a moment we're going to need to use our the reason why, Speaker Greg, is we're
okay.
We're going to want to put our protractor over this and measure the angles, right?
Yeah, I'll just move that. I'll just move it.
Yeah, just do something that looks cool, or
nice.
Do something that doesn't suck.
I did this, Brendan.
Yeah. Can I see? Andy, you're a little off to the side. Shift it over to the left.
Oh.
Other direction. Yeah, there you go. That's fine. You know what? See what Andy did there? I'll take it. I like it. He's making something for me to look at. Yeah, Jake, that's cool. That works at me. Just kind of give me something. Give me something to work with, okay? I can make allowances for COVID situations. All right. All right, let's do it here. Why don't we track sunspots 730 and 83 up to the surface now? Okay. Up to the surface, but no further. There. Okay, there. Something like that. Notice I extend the lines out really far. Make sure that they intersect at the surface of the star. Now we need to try to measure these angles. I'm going to get the squishy paper out from underneath here. Sorry, dying over here. All right. Let's take a protractor and let's measure this angle. So we have to put the whole of our protractor at the vertex of the angle. Then we pin it with our pencil and we spin it until 0 degrees lines up with one of our arms there. So I'm going to spin until 0 degrees perfectly matches, and then I'm going to clamp it down. Now there are two angles to read from, but you can see that our angle is clearly less than 90 degrees because it's less than a box, right? So I'm going to measure to the nearest degree and say I'm probably about, well, 74 degrees roughly. Probably could have done that a little bit better, but I think it was about 74 degrees. Okay. Now, let's try to measure this angle. The compass at the vertex, the angle, and then we pin it, clamp it down and spin it. And this one came out pretty much right at 60 degrees. So I'll write that down in here. Now I want to finish up, figure out the time interval between the sunspots. So how many days would you guys say went from 8:10 to 8:16? What's our time window there?
10 days.
Not 10 days. Try once more.
6 days.
6 days, right? 16 minus 10 is 8.
I
Okay.
thought you meant from 8:8 to 8:18. Sorry.
Oh, that's okay. No, that's fine. Just because we want to know what I didn't specify, so you're correct. I wanted to know the time interval between the sunspots that we tracked. In other words, how long did it take my spot to go from this position and rotate to that position? Okay. Hold on, I gotta check this chat log here. Ooh, no, I've unshared. I'm gonna be screwed. No. Ava, it's very hard for me to check the chat window when I'm in phone share mode, and I just screwed this thing up probably. So this is gonna be a big delay here. Oh, fuck. Yeah, I can't, it's hard for me to check the chat window when I'm on share mode here. Yep, and I lost it. So now I've got to restart my phone. Great. Okay. Guys, while you're at it, why don't you see if you can figure out the time interval for spot B? What's the interval between these two spots, between 7:30 and 8-3? How many days would that be? This better freaking work, or I'm gonna have a mental conniption.
4 days.
4 days, very good. All right, we're back. Jesus, K. Rice. All right. So let's take a look at what we had here. Up here from 8:10 to 8:06, we had an interval of 6 days. This is 7:30, right? That's July 30th. July 31st is 1 day. 8:1 is 2 days. 8:2 is 3 days, and 8:3 is 4 days. So this has a time. Sorry, Joel?
Isn't there only 30 days in July?
30 days has September, April, June, and November. All the rest have 31, except for February, which has 28. That song never made any sense to me either, but no. July has 31 days. You ever heard that song before?
Yeah.
Okay.
But I'm almost as old as you, so that was like
right
about 67 moons ago.
The young kids have like The young kids have something they do with their knuckles, but that don't make no sense to me.
I know that song.
You know the knuckle one?
No, I know the song you sang.
The
Well, I'm
knuckle
sorry,
thing
you
makes
know the
sense.
song?
I know the song that you just said.
Oh, okay, cool. All right, cool.
I do different things with my knuckles, like land features, like Hidden Valley Ranch salad dressing or something.
Oh, what? You're gonna have
Yeah.
to tell me that one sometime.
I don't remember it. It's an acronym.
Oh, okay.
I don't remember acronyms. The Army hated me for that.
Yeah, that's kind of counter to the point, right? Okay, guys, we have to find our angular velocity in degrees per day. So we have 74 degrees divided by 6 days. And that'll give us our degrees per day. So do 74 divided by 6, and that's 12.3 degrees per day. And those are my units, degrees/days. Let's do this one. 60 degrees in 4 days is what, 15?
Yes.
And we'll make it 15.0. We now have to take the average of these two. So let's average. Wait, did we do that right? That seems weird to me. I normally don't get one that high.
Was it 15.0 days?
Yep. This is going to come out weird, but all right, let's see. Let's take the average of those two. So we have 12.3 plus 15.0 divided by 2 is 13.7 degrees per day. Let's now go over to our second page. We're not going to do a C sunspot. That's too much time. Our average angular velocity is 13.7 degrees per day. Okay, we now have to calculate the synodic period. And as I explained before, the synodic period of your sunspot is 360 degrees divided by your average angular velocity of 13.7 degrees per day. So let's divide those up. 360 divided by 13.7 gives us 26.3 days. This is not the true rotation period of the sun. This is the so-called synodic rotation period. Let me see if I can explain that. As we observed our sunspots, we were not stationary, but
Wait, what's the other one?
All right, what's that, Andrew?
What was the synodic day? I didn't get that down.
The synodic period, just do 360 divided by the average angular velocity. 27.3 days. Degrees cancel out.
All right, I got it.
Okay. So here's the deal. During the time that Earth was, during the time that our sunspot was rotating, Earth was in motion around the sun. Earth moved a little bit in its orbit as we were tracking the sunspot. That means we didn't actually get the sidereal period, the time for a sunspot to rotate, but we got the time for a sunspot to line back up with Earth. We can use a similar formula to the one from class to calculate the sidereal period. We're going to treat the sunspot like an inner planet, like Mercury or Venus. And if we do it in days, the sidereal period is 365.25 times the synodic period over 365.25 plus the synodic period in parentheses. That's our formula. So we'll calculate the sidereal period. Oh, by the way, let's put down for our synodic period 26.3 days. Okay. And now we can calculate the sidereal period. 365.25 times 26.3 days over 365.25 plus 26.3 in parentheses. 365.25 times 26.3 divided by open parentheses 365.25 plus 26.3 close equals 24.5 rounds to the correct answer of 25 days, which is the true rotation period of the sun at its equator. And we rounded back to 2 sig figs at the end. Okay. What you can do for me is you could submit this page and this page. If you have a piece of tracing paper, which I knocked on the floor, go ahead and submit your tracing paper. If you made a model of this, you could even submit that if you want. Just send me what you got, okay? And that concludes lab number 8. Hey class, which lab are you going to submit this to today?
8.
That's right. You're going to submit to lab 8 because this is lab 8, okay? Lab 8, boom, boom, thumping techno, lab 8, thumping techno. All right, I don't know what I got to do to make you remember this, but it's lab 8 that you're going to submit it to. And thus concludes the rotation of the sun.